just want to point out first that we did not develop this instrument first thinking about Phobos or Deimos, but once talking with Pascal and some of my colleagues at JAXA and science community in Japan, we realized that given how small we've been able to make a system and the science capabilities that it brings, it could very well be used in the next upcoming missions, starting with MMX and hopefully with some of the concepts that we have been discussing here the last couple of days. So, so I'm going to start talking a bit about LIBS, because I'm sure most of you don't know much about it, and I'm going to give some examples of the things that we can do with LIBS, and I'm going to end up with a couple of concept ideas, just notional ideas of how a system like this could fit into the missions that we're thinking. And so, first off, LIBS stands for laser-induced breakdown spectroscopy, and the whole point here is to deliver enough energy into a sample that you can make a plasma. You can boil it, vaporize it, and make a plasma, and then read the emission of the plasma when it cools down. Okay, so the plasma is a soup of everything that is in the sample, all the electrons, ions, and molecules. And when it cools off, which is something that happens pretty quickly, things start to go back to normal states and start to emit light at very specific wavelengths. And so the first thing that happens when you shoot a laser is that you have a continuum background, and something like this, not very informative, and that's because there's combinations of ions and electrons that are making all this noise, if you want. But if you wait a little bit, you start seeing that some peaks start to emerge. And if you wait enough, these peaks start to be resolved. And this is where you can start doing your chemistry. And some of the things that you can see here is not just ions and natural species as they decay, but if you wait long enough, you're patient enough, you can see molecules as things recombine. So, so you see clearly that there's a lot of interesting information here that you can get with just a single shot of a pulse of a laser, okay, in a sample. And this is a view of what happens with the plasma when you let it cool off, and you can see clearly that very quickly in the beginning, all you have is bright light, and this is all that background continuum that we were seeing in the last slide. But if you wait a little bit longer, you start seeing that it decays, it cools off, and this is where the science can be done in LIBS. So LIBS is working on Mars as we speak. MSL carries ChemCam, which is a masked instrument, and it has a telescope. So, so what it does is shoots a laser in a rock, and it collects the information from the plasma at a distance. Okay, and it's working anywhere from 2 meters to 8 meters, roughly. And so what happens with LIBS is that you're actually making a little crater on your sample. Okay, you're ablating nanograms, picograms, but nonetheless, you're still making little holes. And this is what happens before, and this is what happens after. And for example, ChemCam is doing, this is a point scan technique. So the laser spot on MSL is about 200 to 500 microns. Okay, so so it's a very point scan technique, but it's very fast. So you can do single shots, and the shots last nanoseconds. So so you can actually pulse your laser pretty high repetition rate, and you can start doing raster scans or mapping like you would do with any other technique. Albeit the spots are pretty big in the micron size scale. So so this is the very first spectrum that ChemCam took on Mars, and things usually all the emissions that are interesting happen between the UV and the near IR, and as you see, like elements emit at different and very specific wavelengths. So we do know which wavelengths they are. So all we have to do is to compare our data with databases, and we can start making identification of elements, but not just identification, and then you can also quantify how much of the elements are there, and you do that by looking at the intensity or the width of the emissions. And I'll go into that a little bit later in the presentation. So the instrument that we have developed with my colleagues in Belgium, it's a very compact system. So ChemCam, the one on MSL, it weighs about 12 kilograms, and part of it is that because it's working on remote distances, so you have to have a big telescope or teleobjective if you want. So things start to get bigger, but we're thinking about close-up applications, and for that you can get things down to the size of less than 2 kilograms, including batteries. And we've been able to implement a pretty smart laser design and make a system that gives information that ChemCam is getting on Mars, but it's way smaller. But not only we'll be able to trick with some of the circuits that trigger the laser, and what we've been able to do is to actually look at those different windows of time that I was showing early. So while ChemCam can only do elements, we can start looking into molecules as well, and that gives us, I think, an advantage. We're not comparing with ChemCam, which is a different application, but as far as LIBS systems goes, there are not too many that do this kind of adaptive scanning of different time regions. So we just finished putting this together last May, and the first test and only test we did in June, and this is it's a vineyard. So that was the application that we developed in this for, and the vineyard. The winemaker wanted to see that what happened to the soil over the year, and different patches on his terrain had different soil compositions. And instead of having to go every month and get samples and take it to a lab, he wanted a system that he could just deploy easy and get data on the fly about what's going on there. And so this is single shot Spectra. So with just putting the system down, shoot the system, and with Bluetooth we can control it from a tablet or from a cell phone. And we could see in this spectral region, we can see things like calcium, sodium, and hydrogen. And this guy's terrain is a little bit in the volcanic side, hydrothermal alteration, so there's some lithium as well. And now if we wait a little longer and we start seeing neutral species like carbon here, and peaks start to getting wider, but we still have resolution enough to see hydrogen and carbon in the same shot, which is important for looking at water content and organics as well in this soil. And another sample we could see in the single shot again, not only the carbon but also some elements, and of course hydrogen again. And a different application of this instrument that we did, and this is back in the lab, and we had some oil sands from an oil company, and they wanted to see if we could detect hydrocarbons using LIBS, right? So of course, again, if we play with the times, and we can see a lot of oxygen in the sample, but also start seeing the cyanide groups in these samples, more neutral carbon, carbon, hydrogen, and more carbon, more C2, and CH, which is one of the things that is very unique to the samples that they had. Is that the polymerization chains are really unique, and they were trying to see if we could quantify how much CH we had there, and some other. So I don't know if you're looking at the X scale, but I'm just scanning from IR to the UV, and we can see different elements at different regions. So basically, we could scan the whole spectrum and see different things at different times. So that's kind of what we're doing, and some more elements, and some more elements. But I like they show that how rich spectra are in terms of data. So things like iron, they have a lot of lines, so you could actually scan the whole spectral range, and you can see multiple lines of a lot of elements. So you can start doing chemometrics and quantitative analysis very well, because you have a lot of information coming from the spectra. And you do that by usually taking a raw spectrum, which will be the blue thing here, and you know that emissions are not deltas, unfortunately. So they have certain width, right? And it's usually non-symmetrical. So that happens because things don't happen ideally in the plasma. And since we don't know much about plasma, all we can do is just to start figuring out what combination of bands we can split this spectrum in that could give us a good fit to the original spectrum, right? So once you do that, and you can start quantifying not only the intensity but also the width of the band, and that's what you can use to calculate what the abundance is of certain elements of reference. And in this case, we're doing a semi-quantitative analysis. We don't do absolute concentrations because we don't have chemical data to compare this with, and this is very preliminary. But so we normalized to nitrogen line, because nitrogen it wasn't known to be on the sample, but it is in the air. And one of the things with LIBS is that no matter how tightly you focus your laser on the sample, you're always going to make plasma of the air that is around it anyway, right? So you can use that as a normalizing line if your sample doesn't have nitrogen. So what we did is normalizing our intensities to nitrogen, and then we calculate what the different areas of different peaks are, and we can start getting things that we can compare samples against each other based on quantitative metrics. Okay, and this is something that ChemCam is doing on MSL as well, and fairly successfully. Talking with my colleague Professor Kameda in Ricoh University in Tokyo, he's been discussing with JAXA the possibility of bringing a small compact LIBS into MMX, into their Phobos sample return mission, and his idea was to mount a small LIBS system, working distance 0.5 meter, 1 meter, and have it on a gimbal, so he could do a 1 meter scan on the surface. And one of his concepts is that a lot of the samples that may be interesting there are probably too big to be collected and returned, but you still want to see them. So if you land, and this is a picture of the Itokawa asteroid where Hayabusa landed, you see things that, nothing is fine grained, right? And if we assume that Phobos is not all fine grained either, there may be things that you want to scan. So having this capability of having like a adjustable map system could be pretty interesting. And so my take on a sample return mission is a little bit more radical, and working with Honeybee Robotics in Pasadena, we've come up with a concept of an instrument that would do two things. One is it will drill a core of a few centimeters, say 5 centimeters long by 1 in diameter, and it would take it out of the soil of the ground, and through a window will expose it to a LIBS system that would scan it as it's coming out. Not only scan it in the direction of the axis, but also in the perpendicular direction. So you could effectively map the core as it's coming out, right? And as a proof of concept demonstration, we did this. So this system exists already. The drill system, Honeybee has it already, and it's TLL5 right now. So they're doing a good job with that. And we got the core, we got the sample from the basalt from Hawaii, and we mapped it. Instead of moving the laser beam, we moved the sample, same thing. And we get LIBS data. In this case, we were putting, and I'm sorry for the, I don't know why it's not showing the color here, but this is a temperature color for calcium abundance. So we could see what calcium distribution is in this sample just by looking at the intensities of the calcium peaks. And so this is something that we think could be interesting on a sample return, not just Phobos, but of course Mars and even Moon for robots, is that you might take a core, and if what you find is not interesting, you dump it out. For a Mars sample return mission, you're talking about probably $100 million per core that you're going to return, right? So you want to make sure you bring in high quality things. So knowing what you have in there in situ as it's coming out gives you a lot of power to make decisions in terms of what's coming back. And given that we can miniaturize the system, LIBS, and also the drill system into something that it probably be less than 4 kilograms, having this into a mission to Phobos, Deimos, starts to sound a little credible, although maybe far away, but something to think about, at least for us. And of course, thinking about just doing in situ science and of course ISRU activities over there, small systems like these LIBS could be fairly easily integrated with some of the hoppers and all the concepts that we've been seeing here. And of course, eventually for a geologist / astronaut, having a handheld device that can be deployed as he goes around could be something probably pretty interesting. And so one of the goals of me coming here is to learn more about Phobos, Deimos, and from you guys get some of the science requirements that you would like to see implemented into technical devices like this. So I'm open to questions, comments, and discussions, of course, now and after the talk.
Time for a couple of questions.
What is the size of the ALF-EID spectrometer?
Oh, the outfit. So it's about half the projector right there. So something very like a shoebox, small one.
Okay.
And but this is the first iteration of the system, and it's kind of long, like a pistol size. But we're working on something that will be more kind of like flat and more compact. And yeah, I think that the mass is somewhat more important because you can always reduce volume inside it. The mass is less, is 1.5 kilograms without batteries, so it's fairly easy to bring. Yeah.
Any other questions? Okay, thank you, Pablo.
Mm-hmm.